Yeah, so this is a joint work, I think I'm going to say, with Alexis Prévost, who's from nearby University of Cologne, and Pierre-François Rodriguez from Imperial. I mean, he will soon move to Cambridge. And so, okay, let me first fit the setup I'm going to work with. Let me know if it's, if you cannot read, I can write larger. So I will consider a graph. I will always assume that it's transient to be able to define my Gaussian free field. Let's see if this works. And I'm going to put two assumptions on my graph. The first one is about the volume growth of balls. So let's say my ball, their volume, so this is the cardinality, this is the bar here is the cardinality. It grows polynomially fast, so up to some constant here, and with some exponents that are denoted by t. Okay, and I'm going to do a second assumption, so it's transient, so I can define a simple random walk on it, which is transient, and so has a finite green function. Okay, so I'm going to assume that my green function associated to my random walk on this graph, so it's just a simple random walk on the graph. I jump to a neighbor uniformly at random, let's say. You could add some weights, but it's not. Oops, that's a minus. Decays polynomially fast so here R is the distance. Decays polynomially fast to infinity. So if you go far away, your green function goes to 0. And so typical example would be to think about the D, D larger than 3. And then A is just D minus 2. It's a diffusive random walk. You can fix this example if you want for the talk, but there are many other examples. For instance, you have some fractal graph or some K graph. So for fractal graph, D does not need to be an integer. If you think about things like Sierpinski carpet, then D is not an integer, and you still have this decay, this polynomial decay of the green function. Okay, so on this kind of graph, I mean on any triangle graph, I can define my GFF. So I guess this audience will know what the GFF. Let me just write it. So phi x is a Gaussian field centered, and the covariance of my Gaussian field is a green function. This one. Okay, so usual discrete GFF on my graph. And so in particular, under my assumption, this just means to constant, this will decay as a distance to the power minus 8. So the covariance, so this is a strongly correlating model because its correlation are polynomial, okay, under my assumption. Okay, so this is the Gaussian free field part of the title. Let's go to the metric graph part of the title. So GFF on metric graphs. What does it mean? So there's two possible ways to define it. So you need to fix some parameters. So I want here to define a percolation model. Here I have some critical clusters and there are clusters of percolation. So you have some easier and harder way to define it, and the harder one is the metric graph one, but it's the one I'm going to study today. The easiest one is just the level set one. It's just you fix some level h, and you look at all the points where your field is above h. So h is some kind of height. Okay, you imagine your field is, I don't know, water. The height is water, the field is some mountains, and if you increase the level of water, so increase the h at some point, if it's low enough, you will have like a lot of land, a giant continent, and if you increase it enough, you will have only small islands here and there. So this is the level set percolation. This is not what I want to look at. I want to look at the metric graph percolation. So what does it mean? It means you need to add a bit of randomness to your GFF. So you open each edge, let's say xy, independently, and with probability, which is given to you by the following formula. It's 1 minus exponential minus phi x minus h. I get the 2, it doesn't matter. Phi 1 minus h. Yes. Okay. So, okay, let's look at what this means. it means, so this is the positive part. So this is a 0 if you're negative, or it's phi x minus 1 h if phi x is larger than h. Okay? So let's say that one of the two ends of my edge has a negative value for the field. So if phi x, for instance, is smaller than h, then this is 0. Okay, so it's exponential 0. It's 1, so the probability is just 0. Okay, so the moment you have one of the two ends which is below h, you will never open. I'm never sure. Okay? And if the two ends are above h, then conditionally on the field, you apply this rule independently for each edge. Okay, and you try to open more. So it's a subset of the previous percolation that I was explaining already before, about when you just declare each vertex open with a certain probability.
So
yeah,
was the intuition that if both are very high, it's very probable that they are open?
It's the other way around.
Huh?
It's the other way around. If the you mean if the field is very high? Yes, yes. If the field is very high, it's really likely that they're open. And you will see with my second definition now why it's the case. So this is, let's say, like this is to see it, it's really a usual discrete percolation model. Okay, open each edge with a certain probability. It's more complicated because you have the dependency on GFF, but it's the usual discrete. But you can also see it as a continuum percolation question. This is where the metric graph comes into play. So instead of saying I open it with this probability, what I do is I take my edge, xy, and I have a certain value for phi x, okay, and another value here for phi y. Yeah, let's say this is level 0 maybe. Okay, and then I replace this edge, which was just now the points x and y, by really a continuous interval. Okay, let's say of 1.5, depending on what kind of normalization you take. Let's say of 1. Okay, and if in this continuous interval, you can do a Brillouin bridge between these two values. So let's say I add a Brillouin bridge like that between these two values. Okay, and so this Brillouin bridge, it means that now for each point inside my edge, I have a value for my GFF, okay, which has been extended by this Brillouin bridge configuration, independent Brillouin bridge on each edge. Yeah, and this is a natural notion, I'm not going to explain more, but there's a natural notion of the GFF on this metric graph where each edge has been replaced by a continuous interval. Okay, and this probability corresponds to what? It corresponds, let's say, h is equal to 0 here, and it corresponds exactly to the probability that this Brillouin bridge stays above my level that I fixed. Okay, so it depends on the extremal value, and then it's just a Brillouin bridge computation that gives you this formula. And so you see that if the field at the extremities is very high, then the Brillouin bridge, it will need to go very low to be able to hit this barrier here. Okay, so it will be unlikely, it will be very likely that the edge is open, but it can happen. Okay, and so we want to study percolation of this model. So you have the usual question, like for which h does E larger than h, so these are, let me maybe put some notation here. E larger than h, these are all the clusters of the open edges at level h. So a set of open edges, let's see it as a discrete model to simplify. Okay. And so which depend on this parameter h, and let me call kxh. It will be the cluster of x in my level set. So percolation question, you want to know whether for which edge does my level set percolate. So meaning I have an infinite cognitive component. Okay, so you have critical parameters to that, so I need to be careful about in which order this is a sub, okay. You have a critical parameter, and this is the same as for Bernoulli, just now the h can be take any real value instead of just being between 0 and 1. And it's I mean, it's not clear whether it's finite a priori or not. It's much harder than for Bernoulli, but it has been proved. It's non-trivial. And maybe let me just do a small remark: is that when h increases, this set becomes smaller and smaller. So it becomes harder and harder to percolate. So it's the opposite as for Bernoulli. For Bernoulli, when p increases, it becomes easier and easier to percolate. Just small mental gymnastics to do sometimes. And then once you've understood this, so you understood a bit what the critical parameter is, let's say, then you can ask what is the behavior at criticality or near criticality. So how does my model look like at the critical point? For instance, you can look at, I don't know, a two-point function. You know, so let me write it like that. At level h star, what is the behavior of this? So yeah.
In a general graph, the existence of this h star, is it free or?
It's not free on ZD.
Okay.
So I'm going to comment on that.
Okay, yeah.
But it is not. But let's say it's not much harder than ZD on this one. Let's say it like that. And so you can ask like a two-point function or like a radius. So what is the probability? Let's say that 0 is connected to the ball at distance n at criticality, and all the other kind of quantities that let you understand the geometry of your clusters at criticality. And the reason why we are interested in this model of the GFS geometric graph instead of other model is because we are able to answer this question, which usually we are not. Okay, so usually if you take a model, so this model is strongly correlated. And contrary to Bernoulli, you have some polynomial correlation, which comes from the polynomial correlation from the GFF. And so this makes, I mean, already Bernoulli, you don't understand it in a lot, in like the most interesting physically dimension 3 to 5. Okay, and for this kind of model, you would have no hope in general to understand anything, and it's much harder than for Bernoulli in generality. But it turns out that this model has a lot of integrability and lets you compute stuff. So that's what we want to look at. And once you understand this model better by universality, you may hope that you can understand other models with the same kind of correlation better. Okay, that's the motivation. Okay, so let me answer your first question: why does it percolate sometimes, and why does it sometimes not percolate? So this model I haven't mentioned was introduced by Titus Lupu in 2016, and the first result, or almost the first result that we proved about this model is the following explicit formula. So this is I mean, maybe let me say I will often use also KH. This is KH0. 0 is the origin. I mean, you pick a point that you want just to avoid having an extra thing. So this is another way to write my two-point function. This is the probability that 0 and x are connected. Okay? So the probability that 0 and x are connected turns out there's an explicit formula for this. Okay, so it's some arc sine of the green function divided by some square root of green function, blah, blah, blah. But what matters about this formula in our context is that, okay, you see here the green function is just, this is between 0 and 0 and x, so this is of constant order. And this one decays as a distance to the power minus a, and so an arc sine of t, as t goes to 0, this is like t. Okay? So as the distance goes to infinity, this becomes to constant like the distance to the power minus a. Okay? But at level 0. And a specific level 0, so there's some kind of symmetry in the model that lets you derive this kind of, this comes from the symmetry of the Gaussian field above 0 and below 0, and plus a Markov property. I'm not going to go into this detail, but this is why level 0 is particular for this model. And so if you know a bit of percolation, you know that, okay, if I have a two-point function, and this two-point function goes to 0, turns out it's polynomial fast, but doesn't really matter, then it means that you don't have percolation at this level. It's a general argument for percolation that works for most models. You need basically uniqueness of the infinite cluster. And it tells you that at this level, basically, it's intuitively just if you were to percolate, then you could connect 0 and x easily by just connecting them to the infinite cluster. Okay? And since you have uniqueness on this kind of graph of the infinite cluster, once they are both connected to the infinite cluster, which doesn't cost much, they are connected together. Okay, so the fact that this goes to 0 tells you that you cannot have an infinite component, so you do not percolate. That's the idea behind it. Okay, so on this kind of graph, there's a bit more. Like the argument does not work really. It works on city, but yeah, you cannot just deduce it, and there's other ways to do it, and we did this. So this is with Alexis Prévost, and myself and Pierre Rodriguez, and we extended it to this class of graph using other tools. I'm not going to go into that, but it's true in the general setting that I have here. And so this is first part of the coin, okay? At level 0, you do not percolate. And it turns out there's another part of it, which will come from another result, which is partially due to Titus as well, which tells you that this is actually optimal, and this is the critical point. So what you are missing to prove that is to show that at negative level, you do percolate, at any negative level. Okay? And it turns out that it's true. So let's see. So there are different ways to prove that. I'm going to present one way here. I mean, I'm not going to go full proof, but explain the idea. Which is nice because it gives you like a geometric interpretation of what exactly is your infinite connected component. Okay? So this is due to the fact that there are deep links between this model and the model of random interdecimals. Which is a model from Friedman. Okay. Correct. 10 years. So, okay, do you want me to define interdecimals?
Yes.
Okay.
I've heard talks about it, but I can't recall.
Okay, let me do it. Let me go through it. So, I'm not going to define it properly, but I'm just going to explain what it is.
Like, I'll probably remember once you start. But I've seen it in talks before, just that I can't think of it.
Yeah, I'm just going to go quickly through it then. So basically, random interdecimals is a union of random walk. So each of these trajectory here is a random walk on your graph. Okay, run until infinity, and they are all independent of one another. Okay, and actually they are doubly infinite random walk. You also run backward in time to infinity. Okay, so you don't have a starting point. You go forward and backward in time to infinity. And okay, this random walk, you have actually only finitely many of them that hit a given set. So if you fix a box, let's say this box, these are all the trajectories that hit this box. There are like 3 of them in my example. Okay, but overall in all of RD, you have infinitely many of them. Or ZD, sorry, you have infinitely many of them. Okay, but in a given box, you have finitely many of them. And so this is this union of random walk trajectory. This random union of random walk trajectory. The number is actually Poissonian, so it's like a Poisson point process in reality. And it is denoted usually by I for interdecimant, and there's a parameter U. So what is the U? U is a parameter that controls the number of trajectories that you have that hit a box. So you have a Poisson number of trajectories that hit a given box, and this Poisson has parameter U times something that depend on the size of your box. Okay, so the bigger U is, the more trajectories you have in your box. Okay, but still finitely many. And so this is a formal definition. Let me give you like another way to define it, but it's much less fitting, is that it is entirely characterized by the following property. If I look at the probability that my interdecimant avoid a set k, I fix some set k, and I look at the probability that no trajectory of my interdecimant hit this set k, this is given to me physically by exponential minus u times the capacity of the set k. Okay. So this entirely characterizes the law of IU. It turns out that it's formed by this Poisson process of random walk. And maybe the one question is, what is the capacity of K? So the capacity of K is just the size of my set K from the point of view of the random walk. So the bigger the set K is, the easier it is, the bigger the capacity is, the easier it is for the set to be hit. Okay, so typically a line compared to a box will have a small capacity because it's much easier, that a line of the same size as a box, because it's much easier to go hit a box for a random walk than to go hit a line. Okay. So this is just a way to measure the size. So it's somewhere between the capacity is typically somewhere between the diameter of the set and the volume. It's some kind of intermediate quantity like that. And this U capacity of K, this is exactly actually the number of trajectories that hit K. Okay, so here I have 3 trajectories and I run a Poisson random variable with parameter U capacity of this box. Okay? So I will come back in a moment to the capacity and explain a bit like what are typical capacities of typical set. But let's just take this as a definition for the moment of my interlacement. And so, okay, I didn't give all detail, but is it clear what this model is? Okay. So there's a theorem, which is an isomorphism theorem, which is due from the discrete, is due to Schnitzman in 2012, and on the metric graph, it's due to Lupu, also in the same paper as above, in 2016. So this is, there are 2 versions of this. This theorem, there's a weak and a strong one. I'm going to first present the weak one. So the weak one tells you that the union of the clusters so the sign cluster of my field. What does it mean? It means the cluster where either my field is positive, so it's like E positive, or the clusters where it's negative. Okay, each point is either in a positive cluster or a negative cluster. Okay, and I take the union of all these clusters which intersect my interlacement. So let's say these are my red cluster. So I have my interlacement, and then each point of my interlacement here, it is in some cluster. Either the field is positive or it's negative there, but it is in some cluster, and I just draw the cluster around this point, and it gives me some points. And each point here will be in some cluster, like that. Okay. So this is the union of cluster. Okay, so this is my red set here. All the clusters, the sign clusters, which are hit by the interlacement. And the theorem tells you that this union of cluster has the same law as the infinite connected component of my level set of the Gaussian field, but now at level minus quarter of 2u. So u is the same parameter as the parameters that appear in my IU. And so this is a representation using sign cluster of the GFF plus interlacement of just my infinite cluster. Let me write it like that. This is the infinite part of my cluster. Okay? So why is it infinite? First question. Why is this an infinite connected component? Well, it is just because one trajectory of the interlacement is a random walk, and the random walk is connected, it's an infinite connected component. Okay? And then I just attach to my random walk some clusters that touch it, but this still gives me an infinite connected component. So it's clear that this is infinite. I mean, okay, maybe I should not put the as the union of, let's say, union of all. Maybe not more.
We are running in principle those the field and the interlacement independently.
Independent.
Okay, and then the final.
Yeah. So this the red one are independent of the white one here on the picture, and this second GFF here, this is another GFF. And it's not the same GFF, of course, as the one for which we had the sign cluster. It just has the same law. So we can find another GFF and couple them so that this is exactly my infinite connected component at level minus 2. And so as I explained, this means that this is an infinite connected component because all the random walks are infinitely connected component. Actually, it's unique, it turns out, in this kind of setup that I put above. And so what this means is that, in particular, the interlacement is included in my level set under this coupling. Okay? Because each point of the interlacement is in some sign cluster. And so, and this effect does interpret, and it's somewhat part of the theorem. I'm just rewriting it here. And since this is true for all you're free to choose, you get that you percolate at any negative level, and you don't percolate at level 0, so H star is equal to 0. Okay? Okay, so this is the isomorphism theorem. It's linked to the second Raynight isomorphism for point motion, if you know this. If you just, I mean, it's not exactly that as I stated it here, but it's linked to that. Okay, so as I was saying, this is the weak version of this isomorphism. Now, just describe to me one thing, which is the infinite connected component. Okay, but then you might wonder, but what happens outside of this infinite connected component? Can I describe also my finite connected component of above level minus quarter of 2u? Because you have an infinite one, but you also have some finite one at this. And the answer is yes. So this is the second part of it. So this is due in part to Sinsman, let's say on a certain class of graph, and to us on another class of graph which include the result above. And the second part tells you the following. It tells you that the over cluster of phi positive, okay, so all, by over I mean all the ones that are not the red one, that didn't hit the interlacement, has the same law as this one, this time, the cluster below minus quarter of 2. Okay? So this means that I have some, everywhere here in the complement, each point is in some cluster. Let's only look at the one which are in a positive cluster, so this means the points which are positive here. Okay, they form like some kind of clusters, like that a bit everywhere. And these are exactly the same as looking at what happens below minus quarter of 2. Okay? And below level minus quarter of 2u, since by symmetry this is the same as looking at above square root of 2u, just because you can do minus phi is the same as minus phi, right? And so these are finite, because at level 0 you're finite, so at level square root of 2u you're also finite. So these are clearly finite, which is okay because here you just have only finite clusters. So this is this is a description of this one. So you are much less, because you removed all the ones that were touching the interlacement, but you are now at a higher level. Instead of being at level 0, you're at level square root of 2. And then you can ask, but what are the remaining clusters that are neither positive nor hit by the interlacement? Well, these are all the negative ones which are not hit by the interlacement, and this will correspond to the other side of the isomorphism to what's left. And what are you missing? Well, you have the clusters below minus square root of 2u and the infinite cluster above minus square root of 2u. So what you're missing is the finite clusters above minus square root of 2u. Okay, so everything that is missing here in the picture are just all the finite clusters above level minus square root of 2u. And by symmetry, they are actually the same as this one. Is the picture of the isomorphism clear? Okay. So, okay, but why does this help us? Is a question to describe better my picture. So, but now I've answered my first question. What is H star? H star is 0. So if you were to look, for instance, at the discrete GFF, this would not be true. H star would actually be positive. And so this is really a particularity of the GFF on the cable, the metric graph. And but now you can do more. Let's say you want to look at the probability that phi 0 is smaller than minus square root of 2. So 0 is some given point. Okay, let's say it's, I don't know, this point. This is 0. And you want to look at the probability that phi 0 is smaller than minus square root of 2. Which means that it is in one of these green clusters. And because these green clusters, they are exactly the cluster where your below minus quarter of 2. Okay, so this exactly corresponds to saying, well, there must be some green cluster here around 0. And so what does it mean being a green cluster from the other side of the isomorphism? On the other side of the isomorphism, this means that I need that my field is positive, because I need to be here part of a positive cluster, and I am one of these other clusters that were not red. So it means I do not hit the interlacement. Okay, so I want, on top of that my cluster of 0 is green and not red, so it avoids my interlacement. Okay, so this is just rewriting my isomorphism, but in a very simple case, just for the cluster of 1 point. And now this is where the magic happens. And we number my formula here, which defined my interlacement set. Okay, you can apply it here, but conditionally on the field. The field is independent of the interlacement. And if you do that, what do you get? Well, you keep your indicator that phi 0 is positive, but this probability just becomes exponential minus u times the capacity of your set. Okay? And so this is just a formula on the right applied to this particular Gaussian field cluster, critical cluster, and K0 is a critical cluster here. And now what you see is that since you're free to choose it, this is exactly the Laplace transform of your capacity. Okay, so this is the Laplace transform of the capacity. This costs you nothing because if phi 0 is negative, this cluster is just empty. Okay, so this is the capacity of the M set is 0. Okay. It doesn't cost you anything to have this indicator here. And so you have the Laplace transform of your capacity is the same as this left-hand side. And what is this left-hand side? Well, this is something really simple. Phi 0 is a Gaussian. Okay, so this is just the tail of a Gaussian, and its variance is the green function. So it tells you exactly, this is a really explicit formula for the tail of the capacity. And so since you have an explicit formula, you can compute everything. You can compute its density, you have an explicit formula for the density. And for instance, let me write one formula, which is maybe a bit more speaking to tell you what is happening than this formula, which is not really clear. What does it mean? How big is your capacity? You don't really see it from this. But you can compute from it the tail of your capacity. And it turns out that the tail of this capacity has an exact formula, so it's 1 over pi squared times the green function at 0. The green function at 0 is just the variance of your GFF there. And you have a power. So up to this constant 1 over pi squared blah blah blah, this is 1 over square root of t. Okay, so this answers a question that I didn't ask. Because remember, 0 is h star. Which is, what is the behavior not of the two-point function or this one exponent, which was a natural question, but what is the behavior of the capacity of the cluster at criticality? And this is telling you as precisely as you can what is this behavior. Okay? But of course, I mean, this is not the quantity, this capacity that one is used to looking at, as much as let's say the two-point function or the radius of a cluster, or the, I don't know, the volume of a cluster, all of that. And so one would like to also understand other quantities. So if you look at the two-point function, let's say, the two-point function, you already understand it via Lupu formula. And Lupu's formula for free gives you this is exactly the two-point function at criticality. It turns out that it's criticality. Okay, so you understand already the two-point function and you understand the capacity. And now maybe the next question is, okay, can I understand now what is the typical radius of my cluster? So this is what I now want to explain. Other question before that? So it turns out that there's so if you want to understand the radius, once you know the capacity, you need to know what is the link between the radius of a set and the capacity of a set, which I didn't explain yet. So let me give you just some simple facts. about the capacity of a set, okay, to try to understand better this radius. So, yeah. So let's start with the easiest one, which is what is the capacity of a ball? Let's say take a ball of radius r. So a ball of radius r, it turns out that it has capacity r to the a. So remember this a, like I was assuming that my green function was the distance to the power minus the a from the green function. And the a is d minus 2 on the d. So it's smaller than the volume, but it's bigger than the radius, except in dimension 3, where it's exactly the radius. Okay. And now, what is the capacity of, let's say, a set of diameter r? Okay. And there, the answer is more complicated. You have different cases. Okay. You have the case a smaller than 1, tricky. And then this capacity is also r to the a. This is still up to constant. You have the case a equal to 1. So a equal to 1 is Z3. A smaller than 1 never happens on ZT. But it happens on, let's say, a serpentine cascade, for instance. And you have the case a larger than 1, where it's just r. Okay, so you have a phenomenon that says that your capacity of a given set of diameter r, let's say a straight line, okay, of diameter r, cannot exceed r. And this makes sense because the capacity is subadditive. So the capacity can never be bigger than the volume, and so the volume of a straight line is r, so it can never exceed r. So it gets blocked at this r here. Okay, but obviously it needs to be also smaller than the capacity of a ball, the capacity of a line. Okay, so it cannot also be larger than r to the a. So you have this kind of effect that, okay, which wins between r to the a and r depends on how big is a, and you have this kind of critical behavior when a equal 1, where you have an extra log appearing in the behavior. Okay? So this means in particular that when a is smaller than 1, it's a really particular case where it's as hard for a random walk to constant to hit a ball as a line. Okay. It's a bit like if you know the capacity of a random walk, the critical dimension will be dimension 4, and in dimension 3, it's as hard to hit another random walk as a box, okay, because two random walks will intersect in dimension 3. And here it's the same thing, but instead of having a random walk which is large, it's like even just a straight line is already very large in this kind of fractal curves. Okay, and it's almost very large on Z3. Okay, so what does this tell me? Well, this tells me that the capacity of any set, so in particular, let's say, of my cluster here, okay, this is exactly the same as delta, so let me write delta for the diameter. The diameter of my set to the power a, if a is smaller than 1. And so in the case a is smaller than 1, if I know that I have diameter r, it doesn't matter if I'm the full box or if I'm just a straight line, I still have the same capacity, and this capacity is just my diameter to the power a. This is what this is telling me. Okay? So once I know my capacity, well, I know my diameter. Okay, in this particular fractal case. So this means that the tail of my now diameter is r to the minus a over 2. And the a just comes from this a here, and the over 2 from the square root on the right hand side. Okay, so still if a is smaller than 1. And so that's great. If a is equal to 1, I almost have that. I just lose some logs. So on Z3, I lose some log. This is what it means. Okay, but if you are interested in critical exponent, it doesn't matter. So what does it mean to be interested in critical exponent? It means, let's say you are interested in rho, which is the limit as r goes to infinity of log r over log of my probability that the radius is larger than r. Okay. So this tells you this probability should be polynomial, based on what we saw above, and this tells you what is the exponent of this polynomial. Okay, it's 1 over the exponent of this polynomial, historical data. And this is 2 over a. If a is smaller than 1, so strictly smaller we just saw, the 2 over a just comes from the fact that I took like the inverse here. And if a equal 1, I'm just using some log correction, but this log correction you don't see them in the exponent here, so the exponent is still a over 2. Okay, so I get this critical exponent rho for free. So on the free, this was developed by Ding and Wirth in 20. Full over methods that I'm not going to. Okay, and there's one case that is, however, not working as nicely at all, and this is the most interesting case. This is the case where a is larger than 1, so d is strictly larger than 3 on the b if you want, and then you get that your radius at criticality decays differently. I mean, we don't have the matching bonds for the upper and the lower bound. Okay, and this comes just from this r and r to the a give me an 1/2 and a over 2 when I plug it in my law of the capacity. It comes from this way. So natural question is, but okay, but what is the truth? Does it stick at this minus a over 2 that you were seeing before or not? And well, it turns out it depends in which dimension. So
I guess that, I don't know if I'm
Yeah.
saying this wrongly, but like the emplacements are very thin, but they don't have a lot of volume unless. Oh, no, sorry, we're talking about the cluster.
yeah, but here I'm at criticality, so I do not have interlacement. The interlacement are useful
Yes.
when I'm off critical like that. At criticality, these are just my red cluster, and there was no interlacement actually.
Yes, yes. Okay.
So there are also all these questions have been asked and partially answered also off critical. What is exactly this kind of behavior? But I'm not going to go into that. And so there has been a lot of progress recently on that. So let me just mention the result quickly. So if A is smaller than d over 2, so d was the volume growth of the ball, then rho is still 2 over a. So this is like d3, d4. Okay, you take a d minus 2, and this gives you d smaller than 4. So this was in the end of 23. And then now if a is strictly smaller than d over 2, then we were able to, in particular on z3, to really prove the matching upper bound. So because here, when I'm speaking about rho, I'm not saying that I'm allowed to do some logs. Okay? And here I'm saying, okay, actually, you can remove the logs. And it's really, the truth is really the lower bound is exact. Okay, but it's strictly smaller, yeah, I'm using Z4. But, okay. And then, if you're on ZP now, not nuclear generative, now if you assume D is smaller than 6, you still have that this stays true. And this is Kai and Ding, also last year. And so A is just D minus 2. And if D equals 6, they also prove that rho is 2 over A. But there's some subpolynomial correction. It's not even log, it's subpolynomial. But okay. You still get the correct exponent. And finally, if D is larger than 6, then neither of the bounds above are correct, and the truth is r to the minus 2. And this is the Sokai ding. Okay. This is also okay. So if you know a bit about Bernoulli percolation, this should not surprise you too much. For Bernoulli percolation, the dimension 6 is also the upper critical dimension, meaning that above the dimension 6 you are in the so-called mean field regime, which means that your critical exponents have a fixed value, which is exactly the same value as here. So this is the same critical exponent as for Bernoulli when t is larger than 6. So you're in the same universality class. That's what it means. Okay, and below the dimension 6 for Bernoulli percolation, you expect that you have a different set of exponents. You have no idea what they are, but you expect them to be different. And for this model, you know exactly, at least for this one, let's say, what your critical exponent is. And it turns out that it's a over 2, and it's, you don't expect that it's the same as Bernoulli anymore at all. It's a different universality class, and then when you arrive in the mean field, so d larger than 6, you come back to the universality class of Bernoulli. And actually, this proof here, this last proof, it uses, it's much more complicated, but it uses similar ideas as in the case of Bernoulli percolation in this regime, whereas these proofs are much more different because you arrive at different results.
Can I ask a very simple
No, of
question?
course.
I'm just, so, okay, the D is clear that A is always D minus 2.
Yeah.
I'm just like, if, for what other kind of graphs have this polynomial, like, I don't know, just bigger A means more connected, somehow there are more edges in your graph? Is there any...
No, so so A is always smaller than D minus 2. So you can only be sub-inclusive, actually, so that's theorem by Barlow. And then it's a graph where your work gets slowed down because there are some regions that are hard to exit.
Okay.
So, but if you take any KP graph, you will actually have A equal to minus 2. So you really need to think typically, the typical example is the Sierpinski carpet. So Sierpinski carpet is easier to manage. You do that, then you remove the middle part here, then you remove the middle part of each of this middle part, and so on and so forth. And you do this here again, blah blah blah, at infinity. And this fractal. And if you do a random walk of these fractals, you can define a discrete version of this here. I'm doing the continuum one, but you can define a discrete version of it. Then you have all this obstacle. This is empty. Like all of these are empty. You cannot travel with them anymore. Okay? You need to go around them, and this slows you down enough that you have a different A. In the 3D version of it. Okay, any other question? So, now I guess it's time to go to the last part of the title, which is, I was promising, which is the Hausdorff dimension of the critical cluster. So now we've spoken about two-point function, capacity, radius, what's missing. Well, you can ask maybe one more that you could think about is volume. I'm not going to go into that for time reason, but it's also being studied. But now you can see that you're starting really to understand well the geometry of your cluster, and you have a lot of critical exponents that you can really compute explicitly. So you really have a deep understanding. And so next step is to try to understand the scaling limit. Where do all these critical exponents come from? It comes from the fact that intuitively you have a scaling limit, and then you try to understand actually some information about your scaling limit. Okay, so this is, to be more precise, this is a conjecture by Vanelli Werner, which says the following. So let's say he stated it on Z, so let's state it on Z as well. And let's say that you're below the critical dimension. Okay, so you're in this case where rho is always 2 by the way, that we now know. So he says there exists a unique scaling limit for my critical cluster. So they converge to something in the scaling limit. And it has the following two properties. First is that for any epsilon, there exist finitely many clusters with diameter at least epsilon. So if you take the scaling limit, let's say you take the scaling limit in a box of size 1, okay? And then you look at how many clusters do I see in my scaling limit, and this conjecture tells you have finitely many of a given size. Okay, but you have infinitely many in total if you look at all sizes, but you have finitely many above a given size. And the second one is that each cluster, so still in this scaling limit, has fractal dimension one plus d over 2. Okay, so you want to understand the fractal dimension of your cluster in this scaling limit. Okay, and so the theorem that I want to present now is solving alpha this conjecture. So as you can guess from the title, this is this part of the half. And so still with Alexis Prévost and Pierre Rodriguez, should be out soon. And it tells you the same, so still on ZD, let's say, to simplify things. And it tells you that there exists at least one scaling limit. So we don't prove uniqueness, so that's why I'm saying alpha the conjecture. But there is along the subsequence, you have a scaling limit. But it can depend on the choice of your subsequence. And then if ki, so let me denote by ki, are the clusters in any of the scaling limit, so in particular in this unique scaling limit from above, if you believe in the conjecture, they satisfy the previous conjecture, that is, they satisfy I and 2I above. So there are only finitely many of a given size, and that's how actually you prove that there is a scaling limit, the tightness argument. And the fractal dimension is 1 plus 0, 2. So let me be precise what I mean by fractal dimension here. You can mean either a Minkowski dimension or other. And there are other one in other. And you have some more information. So the capacity of all your cluster is positive. This is now the Brownian capacity. This means that these sets in the scaling limits are non-polar. Okay, the Brownian motion can eat them. And we also have the equivalent, let's say, of the 2-point function. So the 2-point function is just 0 because a given set has 0 probability to hit a point. Okay, they are really fractal sets. But you can look at the probability, instead of connecting 2 points, you can look at the probability to connect 2 balls. Okay? So if you look at the probability to connect 2 balls by one of your clusters in the scaling limit, this is just the probability that they are connected in the scaling limit. This is of order distance to the power minus d minus 2 r prime to the power d over 2 minus. So you have an explicit formula for this connection probability. Okay. All right, so is a statement clear maybe first? So I'm not going to explain the proof, maybe I can just give a hint into a simpler statement from last year. So the simplest statement from last year is about the volume. So, you know, the Hausdorff dimension is a more refined version of a volume, but maybe you can just look first at the volume of your cluster to have an understanding of how big they are. And so this is the theorem from last year. Tells you that let's say that rho is 2 over a, so you invite this nice below dimension 6 case, and you denote by m r h. This is the biggest cluster at level h in your box of size R. So I'm looking not at the cluster of the origin anymore, but I'm looking at the biggest cluster in my box, and this is typically the kind of cluster that will survive in the scaling limit. Okay, the cluster of the origin, typically it will be small and it will disappear in the scaling limit.
And what is h in this one?
H is a cluster at level h.
Sorry, but it's positive.
I mean, it can be anything, so just a definition.
Okay.
Yeah, we actually look at 0. At criticality. And then the statement tells you that, so with high probability uniformly in R, the cardinality of this biggest cluster that survives in the scaling limit is the correct exponent for that is d minus a over 2. Okay? And so this d minus a over 2, by the way, on ZD, this is 1 plus 0. So this is exactly this Hausdorff, this fractal dimension. You can see it here in the volume. Okay. So you get back. This is the intuition behind this Hausdorff dimension. It's not the intuition of Werner, I didn't know any of that, but this is the intuition for now. And so I just have 2 minutes, so let me just do a picture for the lower bound. The upper bound is easy. It's not like Werner already knew how to do it back then. But the hard part is the lower bound. And so I'm going to prove actually that at level minus h is positive here, I have of the correct order of points with constant probability, not going to 1, but just say constant probability. And what is h here? H depends on R. So h is very small, okay, here, when R is big. And there's like a general theory of entropy bonds that tells you that if you can bound it, if you can bound the size of a cluster at a level which is really close to 0, then it's the same as bounding it at level 0. Okay, so let's just look at a cluster which is really close to 0, and the explicit way to make this very close means this. Okay? And then you want to look at what is your biggest cluster at this level minus h. But then what do? You take u equal h squared over 2, so that this becomes mr minus square root of 2u, as in the isomorphism. And your biggest cluster, what is it? It is your infinite cluster, because now you are at the supercritical region. And your supercritical cluster, what it is? What is it? It is just the cluster of the interlacement. And so at this level, your biggest cluster is clearly your infinite cluster. Okay? And so now what you want to know is to understand the size of this infinite cluster for this h, particular h here. Okay, and so the computation is simple. You look at the number of points in your board which are in one of these red clusters. Being in a red cluster means that your cluster of x, let's say this is some x here, the number of points, I'm looking at the number of points that are red, meaning that the cluster hits the interlacement. Okay, this is the volume, this is exactly the same as the average volume at level minus square root of 2u by my isomorphism. Okay? And so this, well, I can put my sum out. Okay? So my sum out, let's say, everything is uniform, let's say just r to the d. Okay? But this probability, now what is it? Well, I can reapply my formula which defines the interlacement, And this tells you, I know what's the probability to avoid the interlacement. So this is 1 minus the probability to avoid the interlacement. And the probability to avoid the interlacement is expectation exponential minus u capacity. And so this formula. But we know what is the law of the capacity already. Okay? So this is, by the law of the capacity, I know exactly what this is, and if you look a bit back in what I wrote, this will turn out to be of order square root of u. And square root of u, by my choice here, so u, square root of u is basically h, up to constant, and so this is r to the d minus a over 2. So you get that, at least in first order, the average number of points via this isomorphism is r to the d minus a over 2. Okay, then you need to show that this, and that's a bit of work to do. I mean, let's say one part of the work to do is to say, well, this is actually just one cluster, because a priori I could have another part of the interlacement here that has nothing to do with the rest. Especially when u is small here, so you don't have so many trajectories of the interlacement. So the interlacement is not so much everywhere. Okay, so this is a bit annoying, but okay, we can handle that. The other thing is that here you will just have like a first moment, you also need to do a second moment method to get a correct thing here. But that is not the most annoying part. The most annoying part is that everything I said so far works in any dimension. But remember, I need to assume here that I was in low dimension. And so what is the problem in what I wrote here is that here I didn't look at the size of the cluster in the box. Because here I'm just asking that x is connected to the interlacement, but what would happen is that x is here, and my cluster of the interlacement, and my cluster does something like that. Okay, and it is very big, let's say like that, and it will hit my interlacement, but far away. But then, these two clusters have nothing to do with one another, somewhat. And this is the case where you need to be in low dimension to avoid this, actually. So that's the idea. Okay, I'll stop here. Thank you.